Before we move on to another topic, I want to do a more substantial example of a linear transformation. Then I want to come back to this example several times in the future. So let's let V be the set of 2 by 2 matrices where the diagonal entries sum to 0. So A11 plus A22 equals 0. We can also think of this as all the matrices of the form A, B, C, negative A, because whatever that first entry is, the 2, 2 entry has to be the opposite of it. And then B and C could be anything. So A, B, and C are real numbers. All the 2 by 2 matrices of this form. Then I want to define a linear operation, a linear transformation. By sending the matrix A to the all ones matrix times A minus A times the all ones matrix. And maybe the first question on your mind is, how do we know that this difference of products of matrices is even going to end up in the space V? Because V is a very special set of matrices. It's the ones where the diagonal entries add up to 0. Well, so let's check. Check that this is well defined. That is, it really ends up where it's supposed to. So if we have 1, 1, 1, 1 times A, B, C, negative A minus A, B, C, negative A times 1, 1, 1, 1, then that is A plus C, B minus A plus C, B minus A, minus A plus B, A plus B, C minus A, C minus A. And that is, in the upper left hand corner, we've got A plus C minus A plus B. So A minus A is 0, C minus B is what's left. And then in the upper right, we've got B minus A plus B. So B minus B is 0. Negative A minus A is negative 2A. Then in the lower left, we've got A plus A, that's 2A. C minus C is 0, so just 2A. And the lower right, B minus C minus A plus A. So the minus A and plus A cancel, we've got B minus C. And, well, looks like we've got a matrix where the diagonal entries sum to 0. So, yes, this definition makes sense. So since C minus B plus B minus C equals 0, then that makes sense. I think all the maps we've looked at so far obviously made sense. But sometimes there's a definition where you don't even see just by looking at it that it makes sense. So sometimes it's worth it to check. All right, next thing that should be on our mind is this linear, because we're studying linear maps. So let's check that this is linear. So if we replace A by something like constant A1 plus constant A2, what does a linear transformation do to that? So constant A1 plus other constant A2 equals a 1, 1, 1, 1 times constant A1 plus constant A2 minus constant A1 plus constant A2 times 1, 1, 1, 1. which is, now we can use the distributive law and say this is the ones matrix times this part plus the ones matrix times that part. So this is 1, 1, 1, 1, C1, A1. Actually, I'll take this C1 out because it's a scalar and we can do that. And then we have plus C2, 1, 1, 1, 1, A2, minus down here C1, A1, 1, 1, 1, 1. So minus C1, A1, 1, 1, 1, 1, minus C2, A2, 1, 1, 1, 1. And then it looks like this is C1 times the transformation of A1. And this is C2 times the transformation of A2. So yes, it's linear. All right, now let's look for a natural basis of the space V and find the matrix of T with respect to that natural basis. Now, given the letters we put in here, the most natural basis that jumps out at me is the one that consists of the three matrices 1 and -1 on the diagonal, zeros elsewhere, and then a 1 in that B position, zeros elsewhere, and then a 1 in the C position and zeros elsewhere. So let's call this B. And let's call the elements of the basis V1, V2, V3. Now, since this map goes from a space to itself, we can use this basis twice. Use it for the V on the left and the V on the right. It's the same space. Might as well use the same basis. So let's find the matrix of T with respect to the bases B and B. Or maybe we could say just with respect to the basis B. Well, we're going to apply T to each of the basis elements and then expand what we get in terms of the basis. T of V1 equals, let's see, 1, 1, 1, 1 times 1, 0, 0, -1 minus 1, 0, 0, -1 times 1, 1, 1, 1, which is 1, -1, 1, -1 minus 1, 1, -1, -1. So the first entry is 1 minus 1, which is 0. Second entry is -1, -1, so we got -2. The third entry is 1 minus -1, so it's +2. And the fourth entry is -1 minus -1, so -1 plus 1, which is 0. This. In terms of the basis, this is -2 V2s, because we've got a -2 up there, plus 2 V3s, because we've got a 2 down there. So this is -2 V2 plus 2 V3. Then what's T of V2? Well, that's 1, 1, 1, 1 times 0, 1, 0, 0 minus 0, 1, 0, 0 times 1, 1, 1, 1. And that is 0, 1, 0, 1, minus 1, 1, 0, 0. It's a minus, and that's a 1. So that is 0 minus 1 is minus 1, 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 0 is 1. So that equals, it's the opposite of V1, so that equals negative V1. And T of V3 is 1, 1, 1, 1 times 0, 0, 1, 0 minus 0, 0, 1, 0 times 1, 1, 1, 1, which is 1, 0, 1, 0 minus 0, 0, 1, 1, which is 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 1 is negative 1. So that equals V1 without a minus sign. So the matrix of T is going to be the coordinate vectors of T of V1, T of V2, T of V3 placed in columns 1, 2, 3 of the matrix. So in column 1 we've got 0, negative 2, 2. In column 2 we've got negative 1, 0, 0. In column 3 we've got 1, 0, 0. Alright, so let's check that multiplying by this matrix is the same as applying the linear transformation T. So recall we showed that T of A, B, C, negative A equals C minus B, B minus C, negative 2A here and positive 2A there. Now the coordinate vector with respect to B is A, B, C. We've got A times this plus B times that plus C times the third thing. So what happens if we multiply this matrix by A, B, C? If we have 0, negative 1, 1, negative 2, 0, 0, 2, 0, 0 times A, B, C, that equals 0 minus B plus C, negative 2A, 2A. Now what entry of the space does that correspond to? So negative B plus C times this. So this is the coordinate vector of negative B plus C is the multiple of this basis element. So let me write C minus B, same thing. And then negative of that is going to be B minus C. And then negative 2A times this vector, so negative 2A there, times that vector, so plus 2A here. And sure enough, this matches. So left multiplying by the matrix of the transformation gives us a coordinate vector corresponding to the same matrix that we get by applying the transformation directly to the matrix. the end.